Chapter 6, ASTROS vs. Nastran Solution 200. Nastran Solution 200 is a structure optimization module. The Nastran you use the central finite difference method to compute the sensitivity of a nonlinear function. So this is the typical central differencing equation to compute the sensitivity of a nonlinear function with respect to a design variable. So we all know the finite difference method accuracy depends on the size of the delta v. For highly nonlinear function, it may lead to incorrect sensitivities, thereby incorrect optimization solution. ASTROS use the complex variable differentiation, we call CVD, technique to generate the sensitivity. So we convert the design variable from a real variable to a complex variable. Then we add a very small number to the imaginary part of the design variable. Then we do a Taylor's expansion. And then from this equation, we can see the partial f partial v is nothing but the imaginary part of this complex function divided by the epsilon. If the epsilon is very small, the high order term in this Taylor's expansion when n greater than 1 arising from the Taylor's expansion are below machine 0. Therefore, the CVD technique can generate numerically exact sensitivity. CVD implementation in ASTROS. All real variables in ASTROS subroutines for computing the nonlinear functions are converted to a complex variable. The imaginary part of the nonlinear function divided by epsilon is the numerically exact sensitivities. So let's look at the impact of stiffness sensitivity on Throttle constraints. The stiffness matrix of C-4, C-3 with the bending stiffness is nonlinear with respect to the thickness. Actually, is a function of T cube. A composite goal-length wing with a nonlinear constraint is optimized by ASTROS and the Nastran solution 200. So this is the goal-length wing structure model. It has a 40 C-4, and each C-4 has a 4-layer composite modeled by the PCOM card. So the total design variable is 4 times 40 equal to 160. First, let's look at the Throttle result of the baseline structure computed by Nastran and ASTROS. You can see they are nearly identical. Now, the optimization problem statement is increase the Throttle speed from 625 feet per second to 1200 feet per second while minimize the weight. And the Nastran solution 200 input file is generated by Zona. So this is the optimization iteration history. And you can see in Nastran they have two optimizers. One is called MSC ADS, and another one is called IPOPT. And both optimizers give a optimized weight which is much higher than ASTROS. ASTROS give a very lightweight design. And so if you look at the thickness of each ply designed by ASTROS is much thinner than Nastran. But both Nastran and ASTROS optimized structure satisfy the Throttle constraint. So this is the decimal crossing zero damping line at 1200 feet per second. So as ASTROS optimized structure, the Throttle speed is at 1200 feet per second. Both satisfy the Throttle constraint, but with very different Throttle mechanism. And the Nastran flutter mechanism is kind of a explosive flutter mechanism. And ASTROS give us the flutter mechanism is a very shallow crossing. Okay, so the question is that is the ASTROS design structure is character one or not? So we plug the ASTROS optimized structure into Nastran flutter solution 145, and then we use 145 to compute the flutter solution. Then it is nearly identical to ASTROS. So this verified that ASTROS the optimized structure is optimum structure because it gives a much lighter weight than Nastran. Okay, then we have another case which is called HA200B, taken from Nastran, MSc Nastran Aero Elastic Analysis User Guide, and it is a forward swept wing, and the structure has a fuselage and the right hand side wing and left hand side wing and a vertical tail. Um, so so we want to minimize the structural weight of the wing and fin, and so we do not optimize the fuselage uh, structure. And the constraint is stress fall between those two numbers under the following trim condition. The first one is subsonic pull up at Mach 0.9 sea level and load factor equals 6G. Supersonic pull up at Mach number 1.2 sea level and load factor is 4G. Subsonic steady rolling pull out at Mach number 0.9 sea level, NZ is 4.8G. Subsonic abrupt rolling pull out at Mach number 0.9 sea level, and NZ also is 4.8G. Entry into a snap roll from level flight at Mach number 0.45 sea level. And we have other constraints. Under the first two trim condition, for the first trim condition, the wingtip twist is less than 1 degree. For the second trim condition, the wingtip twist is less than 0.5 degree. And also we want to impose the aileron effectiveness at Mach 0.9. The sea level is greater than 0.6, and at the Mach number 1.2, and sea level is greater than 0.43. And also we want to flutter constraint greater than 1500 feet per second at Mach 0.9 and sea level, and Mach 1.2 as sea level with 3% of structural damping. And the design variable is that the inboard wing C-bar element and outboard wing C-bar element. So this we call X1 and X2. Also, the beam to model the vertical tail is X3. So we have 3 design variable, and we want to optimize the area. Okay. So the stiffness varies linearly with respect to the design variable. Cross-section area A of C-bar is proportional to the design variable. Moment of inertia of C-bar also proportional to the design variable. First, let's look at the natural frequency of the baseline model, and up to 37 modes, all the natural frequencies computed by ASTROS and Nastran, they almost the same. And then we check the flutter solution. The first one is Mach 0.9 sea level, and this is the damping, then this is the frequency, this is Mach number 1.2 sea level, this is a frequency, this is a damping. So they have a very slight difference. the slight difference of Throttle solution is due to the different unsteady aerodynamic method. The slight difference in Throttle solution of the baseline model may lead to slight difference in the optimized result. Then we want to validate the trim solution between ASTROS and Nastran. The first one is a subsonic pull up at 0.9 sea level, and NZ is 6G. And we have actually we only have a two trim variable, which is alpha, and delta is the canal deflection angle, and other beta and yaw rate and low rate are zeros. So this ASTROS solution, this is a Nastran solution, they are very close. And next one, we want to validate the trim solution of ASTROS at supersonic speed, supersonic pull up at Mach 0.2 sea level, NZ equal 4. Again, we have a alpha and delta, and they are the ASTROS solution correlated well with the Nastran. The third one is a subsonic steady rolling pull out at Mach 0.9 sea level, and NZ is 4.8 G. And we have a 5 trim variable, angle tag, canal deflection angle, side slip angle, and the rudder deflection angle, and low rate. And this is the result of ASTROS. This is the result of Nastran. They also agree well with each other. And the next one is subsonic abrupt rolling pull out at Mach 0.9 sea level. NZ is 4.8, and this time we have a P dot, the roll acceleration as a trim variable, and this is the solution of the two ASTROS and Nastran. And the last one is a snap roll from level flight at Mach 0.45 and sea level, and we have NZ, Q dot, NY, P dot, R dot as the design variable. I mean the trim variable, and this the solution between those two software. Then we look at after we validate the trim solution and the Throttle solution, then we start doing optimization. This is optimization iteration history. Nastran solution is obtained by the version 2008, in which the optimizer is start. And ASTROS also you start as the optimizer. ASTROS requires 16 iteration, whereas Nastran requires 6 iteration to obtain a convergent solution. And then you can see the final optimized solution between ASTROS and Nastran are very close. Okay. However, and then we want to validate that the Throttle constraints are satisfied. So this is the ASTROS, this is the baseline, and this optimized solution. This is the baseline. This optimized solution. This damping and frequency. Then you can see the Throttle frequency satisfied is at 1500 feet per second. So it is satisfied. Okay. And also Nastran also satisfy the 1500 feet per second Throttle speed constraint, and this is the supersonic. Okay, so also satisfy the 1500 feet per second constraint. And then we look at the stress in all the C bar element, and this is ASTROS at this trim condition, and both ASTROS and Nastran satisfy the strength constraint, and also the wing twist angle must be less than plus minus 1 degree, and ASTROS give a 0.3 degree, Nastran give 0.46 degrees. Both are satisfied. Okay, and this the supersonic pull up strength condition. Again, both ASTROS and Nastran satisfy the strength constraint, and also the wind twist angle less than 0.5 degree. Both optimized structure satisfy this constraint. And the next one is steady rolling pull out. Again, the stress in the stress in all C-bar elements satisfy the strength constraints, so as the abrupt rolling pull up, and also snap roll from level fly, and they are all satisfy the strength constraint. Okay, the optimizer in Nastran after after version 2008, they replaced the dot by MSADS and IPOPT. So after Nastran version 2008, the optimizer has been changed, and the dot and big dot algorithm is from Vanderplat R&D Inc. And are not available in the MD Nastran after 2010 release. However, the dot and the big dot algorithm can be found in earlier release. So let's look at after 2010. What's the impact of the optimizer to the optimized solution? So you can see 2008 and the 2012, the weight is higher, and also the design variable solution are very different. So apparently, the optimizer has a big impact on the optimized solution. So the 2010 we use MSC ADS. Okay, the conclusion of ASTROS versus Nastran solution 200. All sensitivities in ASTROS are computed either analytically or by CVD, that is numerically exact. To compute the sensitivity of nonlinear function, Nastran solution 200 employs the finite difference method that may introduce subtraction error. The Z-chain method in ASTROS can include the transonic effect in Throttle constraint evaluation. Such a transonic unstable error element method is not available in Nastran. Nastran solution 200 imposes buckling constraint using an eigenvalue of the whole structure stiffness matrix. We call a global buckling approach. To capture the local buckling mode, like the composite, stiffness crippling require detailed modeling of the webs and fringe of the stiffness by plate elements. This complex structure model is impractical for structural optimization in the preliminary design stage because a large degrees of freedom. It may capture unwanted buckling mode in the non-design structural component. For example, if we want to impose a buckling constraint, and if we want to design the wing skin and impose buckling constraint, but but meanwhile we found out we have a buckling problem from the fuselage, and then because all the design variable is on the wing elements, there's no way for the optimizer to remove the buckling problem from the fuselage. However, ASTROS impose crippling and buckling constraint using a local buckling approach. Analytical buckling equations of plate and bar are used to express buckling crippling constraint for plate and the stiffness. To prevent the global buckling of a stiffened panel bay, the stiffness ratio constraint between the bending stiffness of the stiffener and its attached panels can be imposed. ADS in Nastran version 2012 is a public domain optimizer, but that in Nastran version 2008 and ASTROS is a commercial optimizer. For this HA200B test case, that give a better optimized solution than ADS.